Okay, so today we're gonna finally solve some non-homogeneous PDEs. The last 2-3 weeks we've been just studying homogeneous PDEs. Okay, so we're gonna start with the non-homogeneous heat equation. We're gonna solve it in two ways. The first way is by method of eigenfunction expansion in this lecture 13a video notes, and in lecture 13b we're gonna solve it by method of substitution. Let's begin. Here's an example of a non-homogeneous PDE because there's a g of x and t here. If g of x and t equal to 0, then it just be the regular heat equation. Of course, here our c squared is equal to k, right? So the non-homogeneous usually represents a heat source or sink. Okay. Source or sink. So you can imagine physically on the rod of length L, right? Seen on the x-axis, measure temperature U. You put a little candle here to represent the heat source or something. Okay, candle would be the heat source. Okay. So here we have our. So here's the PDE, equation 1a, and here's our generalized boundary conditions. Okay. At 0, x to 0, and here is at x equal to L. And as usual, we have our initial conditions. Okay. So how do we solve this? Well, we're going to use the method of eigenfunction expansion. And what is that? Well, so the whole idea of method of eigenfunction expansion is we actually look for a solution to a PDE. We expand our solution in terms of eigenfunctions, xn of x. Okay, so let's call this equation 1, where in fact xn of x are eigenfunctions. That's why we call it method of eigenfunction expansion, because we expand our u in terms of eigenfunctions of the related Sturm-Liouville problem. Sturm-Liouville boundary value problem for PDE, the homogeneous PDE 1a, right? This homogeneous PDE 1a with g equal to 0. Okay. So this is with g equal to 0. So that is, right, xn of x satisfies the boundary value problem, the Sturm-Liouville boundary value problem. Put in different color here. X double prime plus lambda x equals 0 with the boundary conditions, right? With the boundary conditions given by the generalized on a1 x of 0 at 0, a2 x of 0, x prime is equal to 0, a3 x at L, so plus a4 x prime at L is 0. Okay, so this is what these eigenfunctions satisfy. Right? Now, so the whole goal of eigenfunction expansion, so we know what these xn's are, right? Xn satisfies, right? Xn satisfies this. Right? So there's a bunch of them. These are eigenfunctions with lambda n, with eigenvalues. So eigenfunctions xn satisfy this eigenvalues lambda n. Right? So the whole goal is to find these functions of time in front of xn of x. Okay, so the whole goal is to find Tn of t. Okay. So how to do that? Well, basically we're going to derive an initial value problem for Tn of t. So initial value problem, remember, from AMA2112 is an ODE for Tn of t. Right? Okay, so let's do this. So let's derive a ODE for Tn of t, function of time. So next step, let's expand our non-homogeneity, Gn of x and t, PD1a, in terms of the eigenfunctions of the associated Sturm-Liouville problems. Let's call it C. So we can do this because remember the eigenfunctions form a complete set. So we can have a generalized where Gn of t, right, is given by the generalized Fourier coefficient expression G of xt xn of x dx over L xn squared of x dx, right? Let's call this 4. Okay. So now, actually these are labeled wrong. Let's put 2, 3, 4, and 5. Okay. Now let's plug 2 and 4 into PD1A. So plug 2 plus 4 into PDE 1A to get what? So we're going to get, so the derivative respect to time, we just hit the TNT function, right? And the derivative respect to x, we just hit the, respect to x, we just hit the xn of x function. Right? So in fact, what we get is summation into 1 to infinity tn dot t times xn of x, right, is equal to c squared, right, summation into 1 to infinity tn of t xn double prime of x. So plus our expansion in, right, of the non-homogeneity. So this is basically our di u di t, right? And this is basically our di squared u of di x. But we know that xn of x satisfies this boundary value problem 3. So in fact, this guy is equal to minus lambda n xn. Right? Since, right, xn satisfies 3, boundary value problem 3, which includes the ODE. So collecting everything into the sums, we get tn dot t xn of x is equal to, so summation into 1 to infinity. There's a common factor of xn now, right here and here. So we get minus lambda n c squared tn of t plus gn of t times xn of x. Okay. So therefore, since these infinite sums on left and right hand sides must, right, these infinite sums are in terms, or expansions in terms of xn of x, then the coefficients in front of these expansions must be equal. That is, this yellow coefficients must be equal. So just bringing over this one term, so that implies that the ODE for, remember, tn dot means the respective time, right? Plus lambda n c squared tn of t is equal to gn of t. Okay. So this is the ODE for time, for tn of t in time, equation 6. Let's call this equation 6. But this is just a linear ODE, right? If you remember, linear ODEs are the form y prime plus p, right, y to f. This has solution, so this is a linear ODE from AMA2112. Anyway, so this is has solution y integral IFC. Remember IFC tower plus over I, was I is the integrating factor in P. Right? So here P is our lambda nc squared, and our right, F is just our Gn, G. Right? So in fact, we can say that Tn of t using this formula. This integral 0 t to lambda n. So our integrating factor here is e to the integral p, which is e to the lambda n c squared t. Okay? So here's this I of c, c squared t, times our f, right, which is gn of tau. Okay, so we need to change the dummy variables plus a constant over integrating factor. Okay? But what's the c here? Well, the c is just obtained. Tn of 0 is just c. So therefore, our Tn of t, just e to the minus lambda n c squared t times Tn of 0, just integral 0 to t e to the lambda n c squared tau gn of tau d tau. Okay, so that's it. Let's call this equation 7. Now what's left over is, how do you find this Tn of 0? Well, it's obtained by this guy right here, equation 1. Right? So we know that equation we get from equation initial condition 1c, initial condition 1c plus expansion 2 implies that, right, so we have u of x and t. This is going to be summation Tn of 0 xn of x to 1 to infinity, right? But this is just equal to f of x, right? So this means that Tn of 0, remember this is by generalized eigenfunction expansion, is f of x xn of x dx over integral 0 to L xn square of x dx, right? Because the eigenfunctions form a complete set. Okay, so let's call this 8. So we're done. Okay, so this is by 1c, this is by 3. So the complete solution to initial boundary value problem happy face is u of x and t is summation into 1 to infinity Tn of t xn of x with Tn of t given by equation 7 and Tn of 0 given by equation that's it. Okay, oops, sorry. Okay, so in the next video we're going to do a specific example of applying the method of eigenfunction expansion to solving non-homogeneous PDE.